Ladies and gentlemen, welcome to the garden. I, like most people, have these thermistors lying around, and because I've developed a use for them, I thought we'd just have a quick look at them before we put them to use. This one is less than a fiver to your door from the usual supplier, and the only things that I know about it from the item description are that it's 25 degrees C, it's 10k ohm resistance, and the beta coefficient given on the side as the B value was 3,380. That's all we know about it. I'm not going to bother calibrating it, but I'm sure it'll be fine. But we could calibrate it and use a Steinhart-Hart model to calculate the temperature. This one is a proper reefer spare part off a marine system, only it never got to the spare parts pile because we kidnapped it on the way out of the factory and did some stuff with it, and then here it is, which is one of the reasons it's got these crappy ends on. But either way, we've got a full data table for this, so we can look up the resistance measured and we can compare that to the value on the table and see what the temperature is. I can't show you that table because it's a proper spare part from a proper actual company. Don't know if it's publicly available, but I'm sure you could find it if you wanted it. And from this, we can plug the values in and we can use the Steinhart-Hart model, and we can then calculate the temperature from the resistance measured on it. Now, of course, the logical question with these things becomes, how do you actually measure meaningfully the temperature or the resistance and then get the temperature from it? Well, one thing that you could do is get your voltmeter, or your avometer in the real money, and you can plug it in, and then we're going to get some value that's going to be around 20. This will correspond to about 20 degrees of temperature. It feels about that in here, but I don't know. I have two thermistors and I don't know what the temperature is. Okay, 12.3 k ohm. So if I hold it in my hand, that resistance is going to go up, down. Temperature goes up, resistance goes down. Wrong way around, moron. And there we go, we can see that dropping. I can't read that because of the angle that I'm at. I don't know if that's any clearer for you or not, but the resistance is dropping as the temperature of this thermistor is going up. What I'll do now is, that was convenient, I'll change to a different camera and we'll hook it up with some components, so then it will be in a position where we'll be able to log it, which is actually useful, because obviously measuring your temperature like this, unless you're mechanicking or something, is absolutely useless. So, back in a minute, don't be early. Okay, so let's get this hooked up in such a way that you'd be able to use it. So what we want to do is, this is a 10k resistor, and this is going to go between ground and the thermistor, and we're going to use the cheapy crappy thermistor, which I've found. Aha. There we go. We're in business. So, what I want to do is go from voltage, which is 5. If you're going to do this on like an Arduino or something, 5 volts. And in, and there's no polarity. So it doesn't matter which way you plug it in, or which way you connect the cables. Then out the other side, and then into the resistor, which is 10k, and then to ground. Now you want to put this resistor value here. This is a fixed resistor, and you want that to be roughly whatever value you expect to be reading around. So you want it somewhere in the middle of the range of the thermistor you've got, which in this case is, what does it do? Minus 20 to 100 or something like that. And then 10k is 25. It's vaguely about right. It'll do. If you've got one of the little ones you get in those Arduino kits, it'll be fine for that as well. I'm just going to become upset by this. I'm going to use this black cable because it's better, more groundy, even though it doesn't actually go to ground. And then this, should you have an Arduino or something, would go to it. So, let's get some volts. And power, no explosion. Boo-hoo. Get you down to 5. 5. Close enough. So, VDC, and then we've got 5 volts there, 5.11 volts, close enough. And if we measure here, which is where you would tap off to your Arduino, we end up with 2.2 volts. And so what you do is you log, or you read this on your analog pin, and then you get your value from 0 to 1023 on something like an Arduino. And then we can use this voltage here. Is that better for you? Maybe it is, I don't know. You can use this voltage here to be able to work out what the voltage drop over the thermistor is, and therefore what the resistance of this thermistor is. So when I hold this thermistor in my hand, the resistance of this is going to drop, and therefore the voltage as a proportion is going to increase on the meter, because we've got two resistors in series, and this is going to be about 12k probably at the minute, and this one is about 10k, so we've got just under half the total volt drop on the 10k. But as I hold it and this drops below 10k, then what we're going to find is that the voltage is going to go over the 2.5 mark, because more than half the drop is here. Yeah, you can see that's happening. That's what you expect. Okay, if you're using one of these thermistors, on something like auto, you're going to be a lot higher than 5 volts, and that's fine. Let's just knock it up to 12 or so, 12.8-ish volts now input, and you can see that you've still got the, it's just because it's a voltage divider, you've just got the same ratio as you would have at 5, only you've got 12. Common voltages for these sorts of things are 5 voltages if you're using something like an Arduino. 3.3 is, you don't normally see them with sensors like these. 12 is a common one, and 24 is a common one, depending on the system architecture that you're using. Right, what I'll do is get this apart, and then we'll go and have a look at it and do some calculations so we can work out what these resistances actually mean in terms of temperature. Right, last thing while we're here, before we go, is just to check how these work compared to one another. This is the cheapo thermistor, and I've got 13.68k on the meter for it. And let's just put these onto this proper thermistor, black to black, because it'll upset me if it isn't, and red to white. Now, worth noting while this is settling itself on the reading, these are different thermistors, they do different ranges, even though they are both 10k at 25 degrees C, or 298.15 in real money. They're going to be slightly different anywhere apart from there. Obviously, the further you go one way, the bigger the difference is going to be. So we've got 13.31 kilo on this one. So now when we go and put these resistances in, we can calculate using 2 different models. I'm going to use a beta model for this because I happen to have the beta value for it and no other data, and I haven't calibrated it or verified it more accurately. And when we do it with this one, I'm going to use a Steinhart-Hart model, and I'll show you where you can get the coefficients for that. But what that will do is you take 3 constants, 1 at each end of the curve and about 1 in the middle, and then we can plug the resistance into that and we should get a temperature. And these 2 temperatures, using different techniques and different thermistors themselves, that are different in design, not just a different thermistor, we should end up with a very similar temperature, which feels like it's, I don't know, little under 20 in here today. Anyway, let's go and see what we get. Here in the digital garden, we're going to take the resistances that were measured earlier and use them to calculate what the temperatures were at the time. So, beta model first, which is the cheapy crappy from the usual supplier thermistor. The general formula for the beta model is this one here, but you notice that this gives us R, and we're measuring R. We don't want R, we want T, so we rearrange it to this equation. And things to note here, the R measured is the resistance that you measure of the thermistor, or you calculate in our case if you're going to do it with a microcontroller. RF is 10,000 for this thermistor, and TRF is 25 degrees C. But you've got to use real currency for these equations, so you've got to put it into kelvins, which is 298.15 K or 25 degrees C. If you're in Fahrenheit, you're on your own, not sorry. And the other thing that's specific to your thermistor is the beta coefficient, which from the item description was 3380. So if we take the resistance measured, which was 13680, that works out at 290.1 K or 17 degrees C, which I know feels like a bit of an underread to me, but whatever. It's it's close enough. It's a thermistor measured with just a cheap AVO as well. So cheap plus cheap. The Steinhart-Hart model that we use for the proper spare part. The equation for this is 1/t equals a plus b log r plus c log r cubed. A, B, and C are Steinhart coefficients, and you can calculate these numerous ways, or you can come to somewhere like this, and I'll put this web address here into the video description, and basically you can just read these values off the datasheet in my case, because I happen to have it, and I've done that for the same temperature range that the beta model thermistor was over. If you don't have the datasheet, there are ways you can do this. What you really want to do is put the top value in, i.e. the highest temperature that the thermistor reads to, the lowest value, and then a value around the middle. But obviously we've got the 25 as 10,000 ohms for both of them, so I've put that in because it's common. And then used -20 as the lower end and +100 as the higher end. This particular thermistor goes beyond that, but that's not particularly important. The ways that you can do this are if you get like an ice bath or something, you can get 0 degrees. If you use boiling water, you can get 100 degrees. And the thing is, these ones are constant, and you know that's what it is, and you don't need an external way to verify it. So, but yeah, if you're going to that level of accuracy, you don't need me to explain to you how a thermistor works. So, good luck. Going back to the calculator, we can then put 13310 because that's what we measured on the spare part thermistor, which gives us 291.8 K or 18.6 C, which sounds more right compared to what the room temperature was. I mean, you can't really say in such an unscientific way if that's more accurate or better than the other reading, but either way, it's only 1.5 K difference, which is a relatively small amount actually. So if we want to put this onto a microcontroller, as discussed, we hook up the one of the analog reading pins to between the thermistor and the resistor, and we use the voltage divider formula. And the R1 here is the thermistor resistance, and the fixed resistance is R2, and our resistivation was 9980. Yeah, 9980 as measured. And then what you do is you solve this for the resistance to the thermistor based on the voltage that you read on the pin. Well, you're not actually reading the voltage, of course. You're on an Arduino, you'll be reading a value between 0 and 1023, and you want to convert that into your 5 volts, and then you convert this to the resistance. And then this is the equation that we looked at for the beta model. If you rearrange and insert the resistance that you're trying to measure, which you're measuring actually as a voltage measurement on the analog pin, this is the equation that you actually want to key into whichever IDE you're using. So just quick check that this roughly works. When we tried it, we had 5.11 volts and 2.19 volts over the fixed resistor, which gives us 17.7 degrees C, and we got 17 using the pure beta model calculation there. So slight difference again. I mean, it could have just warmed up that much being in the room and being handled. Who knows? The next thing we did was to hold it, and the voltage increased up to 2.76 volts, which gives us 29.3, which is just under the 30-ish degrees you expect from a human holding a temperature sensor of any kind. And then we tried using auto voltage, and we put 12.8 volts on, and we measured 6.88 volts, which gives us 29.1. and that's just after we let go of the thermistor. So as you can see, that still works completely fine, but the 5 volts is what you're going to be what you're going to be using if you're on something like an Arduino or other microcontroller. If we go to the Arduino IDE, I coded this program in along with a DHT22 so that I can read a third temperature because I've only got 2 thermistors with me. And nothing really deviates from the equations seen apart from the VREF is 4.985 for the Arduino that I used, and this resistance calculation here is just a rearrangement of one of them because it's more convenient to do it this way because we're not actually measuring the resistance directly. We're measuring a value between 0 and 1023, which is you then have to convert to 5 volts and then convert that into the resistance that you've got. And then all this loop does is just prints out a couple of lines so you know what you're looking at, and then gets the temperature from the DHT, which is on the front fan intake, the beta model, which is on the outlet of the exhaust fan, and the Steinhart-Hart spare part thermistor, which is on the top intake of the case, and then delays for 1 minute. And as you can see, this is what I'm currently getting. The DHT22 says it's 23.8, which, I don't know, might be a bit warmer. Exhaust fan 26.77 and top intake is 25. Now they are clearly picking up a bit of residual heat from the computer being operated, because I can assure you it's not quite that warm in the room. But whenever you're running an electric item like that, particularly one that takes a bit of power, that's kind of what you'd expect. And what happens, I've noticed, is when you start doing things more processor intensive, this exhaust value goes quite a bit higher, whilst the other two stay the same. The next thing you want to do from this is to actually put it out to something and then start to log it in probably something like a CSV format, which is relatively straightforward, but that's for another video. So with that, catch you next time.